Today we're going to talk about information from chapter 10. This is our introduction to geometry. And so it gives us a chance to explore what's going on with points, lines, triangles, and so on. And I will cover 3 sections from the book in this one video, but that should work out pretty well since they all are tied together so well. We start by talking about a point. Now, often I will draw a point as a dot, and it's a fairly large dot, but the reality is points are incredibly small. And from that one point, I might draw a line out, and I'll put an arrow on it like that. And when I put an arrow on, it means it goes on forever in that direction. And so now we need to somehow describe this shape. It's actually called a ray because it starts in one place and emanates out from there. We may have a couple of points on this ray. So to name this, we might call it ray A. And notice I'll put a little one-way arrow on top to denote that that's a ray. We might call it ray AB, saying it goes through those 2 points, something like that. But it helps us describe what that is. If I had the same 2 points, A and B, and I went through both of those but extended forever in both directions, well, that it would be a line. And again, we could call it line AB. We would need 2 points for that, and we'll put a little line symbol above it. You can't really have a line described with 1 point, but 2 points definitely defines that. We might, again, use A and B, and this time maybe just connect them and go between them like that. That's a line segment. So it's a segment or a piece of the line. And we might describe that as, again, AB, but we'd have a line segment above that to denote what we're talking about. And that just gives us a chance to talk about these lines. We've already discussed the equation of a line and how to find the slope, the y-intercept, things like that. Only now we're going to break it down into pieces and look at it from a geometric perspective instead of a slope and intercept perspective. So we've got these different shapes, and we can look at where those shapes are located. There's another little concept that we will look at. If I had a couple of rays, say one going that way and another one going this way to the left, and I won't worry about, well, I do need to name those. So let's call this top one AB, and the bottom one we'll call CD. So I might look at a couple of things, or a couple of ways to look at those lines, those rays even, and I'll use these symbols. The top one is union, and the bottom one is intersection. That's what those 2 symbols mean. So the union, when I hear that word, I actually think of marriage. It's a coming together of 2 things that form a new whole. So we could view a union as a combination or bringing them together. That could be a good way to look at union. Intersection always makes me think of where 2 streets cross, because they always said, watch what you're doing in an intersection and stuff like that as I was growing up. When I think about that, I realized that the intersection itself, if we were to draw one here, and we had these 2 streets coming together, pretend I know how to draw. So the intersection itself would be just this part that connects the corners. Nothing beyond that. If somebody was parked over here, we would not say they're in the intersection. You're not in the intersection until you cross that imaginary line that extends across there. So intersection would be, say, where they actually overlap. And we can use that concept here. We might say, what is the intersection of ray AB with ray CD? So where do those two overlap? So we can come up to those rays, and it looks like from A over to C, we've got overlap. Everything between there would be overlap. So when I see this intersection, I could say, well, that is AC. That's where those two actually intersect. Now, if we were to take the union of, say, AB union with CD, we could think of that as placing one right on top of the other. And what is everything that's covered? Well, that's everything. And that becomes line AB, maybe, with extensions going both directions. So the union, we're combining things together. And the intersection, we are seeing where they overlap. Now, we might even just look at a single line here. We might have A, B, C, and D all sitting on the same line. So what would the, well, let's not do AB. Let's do AC intersected with BD. So let's see what we've got here. We've got AC is the portion that is now in blue, and let's grab another color. Green might not be best. Let's do BD, be that portion that I've colored kind of down below. And where do those intersect? It would be this intermediate region here. So that would just be BC, is where those intersect. But that's just a way that we can look at how items are combined. And so, well, if I take a couple of rays, maybe we'll start with a ray that extends off to the side like this. And then if I take another ray and put it on top of it, but rotate it around this center point such that it's up here, now I've created an angle. And we will have various names for this angle as well. Let me go ahead and label these points. And maybe we'll have a number in the middle here. So we could call this, and the symbol we use looks like an angle, like that. This could be angle B. That would be one way to call this. We could call this angle ABC. We could call it angle CBA. Notice in both cases there, we started at one of the points on the ray. The middle point is where those two rays join, and the third point is the other one. So it's important to note that the middle one in the name always is this point where they meet. And we should probably name that point where they meet. I know we called it B here, but there is an actual math name for it. That would be the vertex. The vertex is where two line segments or two rays meet at that point. And since I put a little 1 in the middle, we could even call this angle 1. Several ways to name an angle. Well, we'll need to measure that angle in some way. And so one of the things we'll use is a protractor, like this. That's the name of this particular tool. And I would say it's awful handy to have one around the house. More than once, we need to get some angles. And let's look at how we measure this one. Now we'll start at this ray BA and we will rotate up through to ray BC. And notice they've got this set of numbers on the inside. That allows us to start over here on the right-hand side and rotate counterclockwise. So this one has rotated through to 50. So this is an angle of 50 degrees. The symbol and the unit that we use for measuring an angle is often degrees. There are other measurements like radians, but we won't worry about that in this class. In this class, we'll concentrate on degrees. And so this one is a 50-degree angle. If we were to have an angle whose ray ended perfectly vertically, like I just drew, that's perfect. Then notice that we have rotated through 90 degrees. And we will put a little square in the corner to denote that's a 90-degree angle. Also notice over here on the far right, we went through 160, then 170, so next would be 180. So if you rotate all the way across from straight right over to straight left, you've created an angle of 180 degrees. Now we have some names for some of these. We've got an acute angle. We've got a right angle. We've got an obtuse angle. And we've got a straight angle. Those are the angle types that we will look at in this class. Now, an acute angle has a measure that is between 0 degrees all the way up to 90. And I should probably cross out that 90 and put 89.99 degrees. It goes all the way up to 90 without actually equaling 90, because once we equal 90, we have a right angle. So anything less than 90 degrees would be an acute angle. Exactly 90 degrees is a right angle. Notice that if we were to rotate from this ray BA all the way over to headed the left direction, we've made a straight line. So that's why we call 180 degrees a straight angle. And an obtuse angle is anywhere between 90 degrees and 180 degrees. So it's bigger than 90 degrees, but it's less than 180 degrees. So we have those definitions, and those words will be used. And so we need to know what we're talking about when we see those angles. And that will really help us understand some shapes and be able to intelligently discuss angles and how far things are rotated. Because if you're working on something with somebody and you say, oh, it rotated about that far, well, their about might be different from your about. And so it can be rather confusing. But now let's take those angles and see what we can do with them. One of the things that we will look at is what happens if we have a couple of parallel lines. So I'm going to define those as parallel. And they're cut by a transversal. Trans is across, versal means sides, I think. So it's crossing the sides, anything that crosses two parallel lines. We can actually understand the size of each of those angles if we're given one of them. Because think about this, if we have two lines that are crossing, like the two I just created, then these on opposite sides have to be the same. Because the the lines rotated through a particular angle about that vertex in the middle. And so if it rotates that angle on the right, it has to rotate that same angle on the left. And we will mark angles that have the same measure with a tick mark or something like that. Those two angles are called vertical angles. Those are angles that are on opposite sides of a vertex. Oh, what was I writing? Opposite sides of a vertex caused by two lines intersecting. Well, by that measure, we could say that the angle on top and the angle on the bottom have to be equal. And I'll put 2 marks on those because they don't necessarily equal the side angles, but they have to be equal to each other. Again, those would be vertical angles. So that has to be equal to each other. That means that if I've got this angle up here by the transversal, that the one opposite it has to be equal to it. So let's go ahead and put some numbers on here. I'm going to call this short one, let's say 50 degrees. And that means if that one's 50, then the one opposite it also has to be 50 degrees because they are vertical angles. So now I've got those two. Well, now let's take a look at what we have here. I have a straight line up here at the top. If that's a straight line, then the full angle has to equal 180 degrees, that purple one there. And if that equals 180 and I've already taken up 150, then this one has to be 130 in order for those two to add to 180. And now the angle opposite that 130, because it's a vertical angle, also has to be 130 degrees. Or we could look at it as, oh my gosh, we're making another 180-degree angle here, another straight angle. So that one has to be 130. And we have names for those too. We have names for almost everything. So if two angles add to 180 degrees, they make a straight angle. I'm going to say sum to 180 degrees, just so I can use a fancy math term. We call those supplementary. Supplementary angles are two angles who add to 180. So that's a word you're going to want to remember. We also have the case where two angles might add to 90 degrees. And they have their own term. Two angles sum to 90 degrees. They are complementary. So you'll need to find a way to remember complementary and supplementary because those terms are used in the homework and regularly. Maybe think complementary starts with a C, supplementary starts with an S. And so it's kind of in alphabetical order. And notice complementary has a 90-degree angle, supplementary has a 180-degree angle. So those are in numerical order as well as alphabetical order. But that can help us anyway. Now, if I were coming back to this, this shape here with the parallel lines, if I were to pick up this top intersection and lay it on top of the bottom intersection, certain angles would be on top of others, right? So this 130-degree angle here in the bottom right would be on the top of the bottom right angle there, and they would be identical. So that must be 130 degrees. The angle opposite it, because of it's a vertical angle, would also have to be 130 degrees. The angle in the top right would have to be 50 degrees to make a straight angle with the 130, or because it's right underneath the 50-degree angle from the top intersection. And the angle opposite it has to be 50 degrees. So notice that all of the big angles in this case are equal to each other, and all of the smaller angles are equal to each other. We have names for all of that as well. I'm going to now label these with a letter. So A, B, C, D, and we'll come down to E, F, G, and H, just so that I can talk about them a little bit more. So A equals C, and E equals G. Oh, you know what? I can just put that A equals C equals E equals G. Those are all equal to each other. But notice A equals C because they're vertical angles. E equals G because they are vertical angles. Now, A equals E and C equals G, we call those corresponding angles, because when you put one intersection on top of another, these line up with each other. So those are called corresponding angles. Now, E equals G, C equals E. We know that, we saw it up above, but also because those are what are called alternate interior angles. Alternate because they're on opposite sides of the transversal. Interior because they are between the two parallel lines. Note this, B equals H, we already saw that. Those are on alternate sides of the transversal, but they are exterior to the parallel lines. So if they're on the alternate sides of the transversal, but between their alternate interior, therefore D equals F and C equals E. If they are alternate sides of the transversal, but outside of the parallel lines, they're alternate exterior angles. So A equals G and B equals H. We've got all these fancy names to say that angles equal each other. But the quickest, shortest, fastest way to remember it is the big angles equal each other and the small angles equal each other. I'm going to come back to the protractor just for a minute, because I also want to talk about something else. I just remembered we have a homework problem that deals with a clock. So the top of the clock is 12 o'clock. We've got 6 at the bottom, 3 on the right, 9 on the left. So those are kind of our basic ones. Notice that this is like two protractors, one on top of another. So I could kind of draw a dashed line here that might be the base of the top protractor and the base of the bottom one. And so if the top one is 180 degrees and the bottom one is 180 degrees, and I add those two together, then I get a total of 360 degrees. That's how many degrees are in a full circle. It's those two half circles. And so that's important to note. Now, one of the problems they might give us in the homework is they might say, well, what if the hour hand starts at 2 o'clock? And let's say that it ends at, 6 o'clock. So it goes from 2 o'clock to 6 o'clock. How many degrees does that go through? Well, let's see. From 2 to 6, we've also got 4 and 5 in here. We go through 1, 2, 3, 4 hours. So that's 4 hours. Out of how many total around? Out of 12. And that equals some measure out of a total of 360. And so now we've got this proportion. We're comparing the size of the smaller angle to the full circle, just like we are with time. And so now what do we do with a proportion? We can cross multiply. So I could say 12 times m is 12m, and that equals 4 times 360. Well, 4 times 360 is 1440. 12m. And now I could divide both sides by 12. Because 12 divided by 12 is 1, I'm left with 1m. And 1440 divided by 12 is 120. So it's 120 degrees, which is, think of 4/12, we could divide top and bottom by 4. And we get 1/3, that's the simplified fraction. And 1/3 of 360 is 120. So that's how we might answer how many degrees an hour hand has gone through when we go from one time to another. You've got a homework problem or two, probably 3, about that. So I wanted to make sure that we talked about it so that you could see it. All right, and that kind of wraps up 10.1. So now let's move on to 10.2. I don't want that layer anymore. I need a new layer. Okay, 10.2. I'm going to go back to some parallel lines here for a minute. We'll just kind of define those as parallel. We'll say we've got this point here and another one, and I'll extend that down. Well, that kind of makes a transversal. I should probably draw the line before I draw the point. So that makes a transversal. That tells me that if I've got angle B here, that this would be angle B there. Those are alternate interior angles. Let me extend another line from B down to the parallel line down below, and we'll call that C, angle C here. Well, if that's angle C, this must be angle C because, again, they're alternate interior angles. Let's call this angle up here A. So if I add these 3 angles together, they make a straight line. So A plus B plus C equals a straight line, which is 180 degrees. Well, now take a look at my triangle. My triangle has angle A, B, and C in it. So that tells me the sum of interior angles of a triangle has to be 180. And that is always true. No matter what triangle you have, if you add the 3 angles inside, they will equal 180 degrees. And that really helps us out a lot. So we might be given an odd triangle here. Might come down like this, some strange shape, maybe. It's not that strange, it's a triangle. Let's even make this one 90 degrees. So if I call this one 30 degrees, I can find the missing one, because that little square down here in the bottom left says that's 90 degrees. I'll call this one A just because I know that A plus 90 plus 30 has to equal 180 degrees. It has to, because the sum of all interior angles of a triangle is 180. So if I combine like terms here, 90 plus 30 is 120. I'm just solving for A. Now I'll go ahead and subtract 120 from both sides. And when I do that, I get that A equals 60 degrees. So we know that because the sum of the angles inside a triangle has to be 180. So that will give us a chance to figure out some of these triangles. Well, as it turns out, we have names for triangles. Notice here, I've copied this straight out of the book. We can see that an acute triangle is what we call the triangle when all the angles are acute. Remember, acute means they're less than 90 degrees. So these are all pretty small angles. Now our next one over is a right triangle. And that's what we get when one of the angles is 90 degrees. We'll use that a fair bit. Right triangles are really good for us. An obtuse triangle is one where we have an angle that is larger than 90 degrees, but of course less than 180. It's an obtuse angle. And then maybe we'll classify them by their sides. If we have two equal sides, we call it an isosceles triangle. And if those two sides are equal, then they're opposite angles. These two down in the base have to be the same. If all three sides have the same length, it's called an equilateral triangle. And each angle measures 60 degrees. And a scalene triangle is when no two sides are equal in length. So notice that we can have an isosceles right triangle. This could be 90 degrees, and each of these might measure 2 feet, say. That's quite possible. And if both of those measure the same, then these angles have to be the same, which actually would make them both 45 degrees. So, because that's what it takes to add up to 180. So this is an isosceles right triangle. It's isosceles because the two sides have equal length, and it's right because one of the angles is 90 degrees. So we can use that classification a fair bit, and it will help us to understand and make sure we're talking about the same thing. We do have, with right triangles, a nice equation that will help us get the sides. So let me go ahead and draw a right triangle again. Maybe this will look a little better, probably not. So there we've got a right triangle. As it turns out, with right triangles, I'll label these sides A, B, and C. There is a formula that describes those lengths. It's the Pythagorean theorem. You've probably heard of it. You may even have the formula memorized. And it's a good one to memorize. It only works with right triangles. But if you have a right triangle, you can use this. And we find ways to make right triangles so that we can. The formula is a squared plus b squared equals c squared. Now, with that particular formula, c has to be on the longest side of the triangle. We call that side the hypotenuse when it's a right triangle. It is the side that is opposite the right angle. So if you go from the right angle and go through the center of the triangle, the side you hit is the hypotenuse. That one has to be C. Now, the other two could be A or B. Those can swap. They don't matter so much, but the hypotenuse has to be C. So if I have a right triangle, and let's say this side is 3, and this side is 4, what would the other side be? Well, I can grab Pythagorean theorem. A squared plus b squared equals c squared. Now, which one am I missing? Let me go to the right angle and go through the center of the triangle. The side I hit is C. So I've got A and B. It doesn't matter which one is A and which one is B. 4 squared is 16. 3 squared is 9. Now I can add those together. 16 plus 9 is 25. Notice I used PEMDAS. I did the exponents before the adding. And now to reverse this c squared, I need to take the square root. And anything I do to one side, I do to the other. And as it turns out, the square root of 25 is 5. And that would be c. So now we found the length of that third side. Maybe they give us a slightly different problem. Maybe it looks, we've got a short side and a fairly long side over here, which gives us an even longer hypotenuse. So I'll go ahead and make that a right triangle. We'll call this 13 and that one 5. All right, so as I start at the right triangle, I go through the middle. The side I hit is C. And these other two are A and B. I'll call this one down here B, just because it felt like a good thing to do. A squared plus B squared equals C squared. We'll call A the 5. I don't know B. C is 13. 5 squared is 25. 13 squared is, let's see, 39, 169. And now I need to subtract 25 from both sides. And I get that B squared equals 144. And I need to take the square root of both sides because I need B. I don't need B squared. And B would equal square root of 144, which is 12. So that would be the value of this side down here at the bottom. And we've found all three sides of the triangle. That's one of the beauties of the Pythagorean theorem. Again, it only works on right triangles, but when you have one, you can find a missing side length. And always start by going from that 90-degree angle through the center. The side you hit is C. Watch out for that. That's always the case. And it's very important that we do that. One of the things that we need to watch out for is whether or not two triangles are actually equal to each other. You'll have some homework problems where it will ask you if two triangles are equal and why. Now, one of the things they might do is they might create a shape that looks like this. And they'll call these right angles. And maybe they'll say that this is 5 and that's 5. And so let's see, what have we got? Now here in the middle, notice these two angles have to be equal to each other because they're vertical angles. And if those are equal, now what have we got? We've got two angles that are equal to each other, that one and that one. And then we've got a side between there that's equal, and then we've got these two angles are equal to each other. So we have an angle and a side and an angle. And notice that when you have angle, side, angle, two angles and the side between them, if those are the same, then the triangles are the same. And so we would say these are congruent triangles. Congruent means they have the same measures. They also would be equal if we had two sides and an angle between them that is also the same. Or if all three sides have the same measure, side, 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 then we have congruent triangles. And you'll be asked, are these two congruent? And tell us why, whether it's side, 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 or angle, side, angle. And so you'll just pick the one that applies, which one of those three. And so you're looking for things even beyond what they show you. Maybe you need to look at vertical angles or something like that to prove that they are identical. Now notice we don't have here angle, angle, angle. And let me show you why. If we had a couple of triangles here, maybe this one, call that right, and I'll call this 30 degrees. And then we've got this one, and I'll call this a right angle, and that 30 degrees. Well, that third angle we already showed had to be 60 degrees because the three have to add to 180. And you can see that those are very similar triangles, but they're not congruent. And if this is an angle, 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 if you've got two triangles that are angle, 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 we call those similar, specifically when they have different side lengths. So I'll call this one maybe a 3, and this will be a 6. Clearly, they're not the same size. They're not congruent, but they are similar because they've got the same basic shape. And so we call, when it's angle, 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 we call those similar. Now that will actually help us do some calculations. If we have, for example, a tree in our yard, well, the one side was much better than the other. Say we've got this tree in our yard and we're standing down here and we want to know how tall that tree is. Well, it turns out that when the sun strikes us at a particular time of day, any time of day actually, our shadows are proportional to our height. The angle made down here in the side is the same. So the angle made with the end of our shadow and the top of our shape is always the same at any given time. And so if maybe I'm 6 feet tall and my shadow is 4 feet long, and I can measure the shadow of the tree to be 24 feet long, how tall is the tree? And this is where the fact that we've created similar triangles comes in, because those proportions have to be the same. So we could say maybe my height is to my shadow length as the height of the tree is to its shadow length. And now we've got a proportion again. When you have a proportion, you can cross multiply. So let's go ahead and cross multiply. 4 times h is 4h. Keep that equal sign in the middle. 6 times 24 is 144. And now I'm solving for h, so I would divide both sides by 4. 4 divided by 4 is 1. And I'm left with h equals 144 divided by 4. Looks like it's about 36. So the height of the tree is 36 feet. I can't get out there and measure the tree with measuring tape. However, I can set up a similar triangle situation and recognize this calculation. Now notice I did height to shadow for both of them. This was me and this was the tree. Well, I could have done my height is to the tree's height as my shadow is to the tree's shadow. Notice both of these are height, both of these are shadows. The top is me, the bottom is the tree. Either way, when we cross multiply, we get 4 times h, and we get 6 times 24. We get the same thing. So as long as you set them up with the same sort of thing on the top, with the same sort of thing on the bottom, this is going to work out well. And you'll be able to calculate, because they are similar triangles, some of these lengths that we wouldn't normally be able to calculate. And that can help us a fair bit, actually. And so think about using similar triangles when you can. Also look for vertical angles to help prove congruency, or even just the measures of angles. And remember that the sum of all the angles in a triangle is 180 degrees. And that wraps up 10.2. So let's take a look now at 10.3, where we're talking about polygons. And we've got several types of polygons, but they're named by their sides. Now, a polygon is a closed shape made of straight sides. Closed meaning it's not all the sides are meeting. And these straight sides all meet at their endpoints. That really well defines what we're looking at. So a circle would not be a polygon because it doesn't have straight sides. But these polygons that I have on the screen do have straight sides, and they all meet with at the end points there. And we name them based on the number of sides. You're familiar, and we just spent some time talking about triangles. Those are three-sided figures. A quadrilateral has 4 sides. A pentagon has 5 sides. A hexagon has 6 sides. A heptagon has 7 sides. And an octagon has 8 sides. A nonagon has 9, and a decagon has 10, but we won't have to worry about those too much. Just know that we have names for those. And so understanding these polygon names will allow me to say, well, say we've got a hexagon. What would be the sum of all the angles inside of a hexagon? And so maybe we would find a way to add those up. It turns out there's a really nice way to add those up. Well, let's do it now. We've got the thing. So I'm going to bring up this polygon here. Let's see, count the sides. It looks like it's got 1, 2, 3, 4, 5, 6, 7 sides. So that's a heptagon. Well, what is the sum of all of these interior angles? If I were to add all of those up, what would I get? There's actually a nice formula for figuring that out. But you know what? We can come up with that formula. What's the sum of the angles in a triangle? Yeah, 180. So maybe I connect these vertices and make a bunch of triangles. How many triangles do I get? 1, 2, 3, 4, 5. Well, 5 times 180 is 900. That's the sum of the angles inside of a heptagon. Let's do a hexagon. Those are kind of fun. So that has 6 sides. I'm going to go ahead and draw some triangles. There's 1, 2, 3. So I've got 1, 2, 3, 4 triangles. And 4 times 180 equals 720 degrees. So a hexagon, 6 sides, has 720. A heptagon with 7 sides has 900. Let's try a pentagon. We'll draw some triangles here. 1, 2, that's all I can do. It's got 3 triangles. So 5-sided figure has 3 triangles, and 3 times 180 is 540. Well, I'm noticing a pattern here. Notice when I had 7 sides, we made 5 triangles. When I had 6 sides, we made 4 triangles. And when I had 5 sides, we made 3 triangles. So I could take the number of sides, subtract 2 from that, and multiply that by 180. And that would give me the sum of the interior angles of any polygon. Well, that's kind of nice. If I had a 10-sided figure, a decagon, well, that's 10 minus 2, which is 8, times 180 would be 1,440. So that would be the sum of the interior angles of a decagon. And we've got this formula that will allow us to quickly calculate it. And we just came up with that on our own by looking at these polygons. I know it's written in the book, but I don't always remember a formula. However, if I know how I can create it, now I've got some more power available to me. And that I think is pretty handy. So with these polygons, one of the things we may have to do is calculate perimeter. So let's take a look at one of these. Perimeter is a calculation we will need, and perimeter is like, how much fence do I need to go around the yard? So it's the sum of the side lengths. So the perimeter of this particular polygon, and how many sides do we have? 1, 2, 3, 4, 5, 6 sides. So that's a hexagon. The sum of the sides of this hexagon are 4 plus 9 plus 13 plus 5 plus 17 plus 14. So when I add those together, we get a 13 here, plus 13 is 26, plus 5 is 31, plus 17 is 48, plus 14 is 62. So 62 inches would be the perimeter of this particular polygon. And you can just type that into your calculator. Now let me show you a little trick here. This might be nice for you. Take that 9 and that 5, and when we add those together, we get 14. And look, that's the same thing down here. If we take this 13 and this 4 and we add those together, we get 17, which is the same thing I've got there. And if you think about it, if there's somebody way down here and they're looking at the building, they would see the 14-inch side. Well, if they're way up top and looking down, this 5 side would mesh so well with that 9 side, they might not even know that the 13 was there, and they would see a 14-inch side. Same thing from this side, they see the 17. Well, if they're coming from that side, they would see the 13 and the 4, and that would be 17. So sometimes it works where you can just take the long side and the other long side, add them together and multiply it by 2. That can work sometimes. So consider that. Maybe it's a good thing to look at. Oh, here we've got it. This is one of those. If I were to maybe, right on this one, I extend that down, we could see that this 3 feet is the same as 3 feet there. And this 6 feet would be the same as 6 feet there, for a total of 9. We would also see maybe that we could extend this way such that this 3 feet is there, and this 4 feet is also over here, for a total of 7. So let's try that little trick. 7 plus 9 is 16, and now I'm going to multiply that by 2, and I get 32. Let's see if that works to add up all the little bits and pieces. So we had, starting at the top, we had 3 plus that little side of 3 plus the 6 plus the 4, plus the 2 that we added together to get 9, plus the 2 we added together to get 7. So this 3 and 3 are 6, plus 6 is 12, plus 4 is 16, plus 9 is 25, plus 7 is 32. That little trick worked. So sometimes we don't get all the sides, but we can figure it out by pretending that we are extending a line through and just add the sides that are parallel to that to get the side that we need. So different ways we can calculate perimeter, but regardless, they would allow us to figure out how much fence you might need to put around that outside edge. Now, one of the things that we need to talk about also are quadrilaterals. We talked about the various pentagon types based on the number of sides, and it turns out quadrilaterals have their own subsets, and they're based on the lengths of the sides. If the 4 sides are all the same length and the 4 angles are all 90 degrees, that's one with which we're quite familiar. That's a square. But those things have to apply. They have to be 90-degree angles, and all 4 sides have to be the same. If the 4 sides aren't the same, but we still have the 4 90-degree angles, that's a rectangle. I know you're familiar with those, but I wanted you to know the definitions because sometimes the problems will say something like, my yard is a square yard, and the length of one side is 12 feet. So if I've got this square and the length of one side is 12, then that means because it is a square, that they're all 12s. And now I can get the perimeter. So you can see that definition can really help. Let's look up here at a rhombus. Notice all four sides are the same, but the angles are different. It's like they took a square and they squished it to the side a little bit. But that's key. A rhombus has all sides of the same length. So when you hear that word, you know what it's talking about. And up here on the top, we've got a parallelogram. Notice opposite sides are the same length. So that's basically a rectangle that's been squished to the side. So that's a parallelogram. Notice that opposite angles are the same measure, regardless of which opposites you're looking at. So that's something we can watch out for. And then we've got this odd duck down at the bottom. It's a trapezoid. And the top and bottom sides, I call it top and bottom here because that's how they drew it. Those are parallel. So we've got two sides that are parallel and the other two are not. That's a trapezoid. Still a quadrilateral, but we call that shape a trapezoid. And that gives us some other features that we can use to calculate stuff. But you need to know those types of quadrilaterals so that you're ready for some of the homework. And now let's go ahead and wrap up. Oh, I've already done everything. I've done the sum of interior angles, which was the last bit I wanted to touch on, but we'd already done that. Okay, so we've talked about everything we need to for 10.1 through 10.3. We talked about points, lines, and angles. And then we extended from angles over to triangles and how the sum of the angles is 180. And then we extended that to other polygons. We also talked about how to measure angles. We talked about congruent triangles, how they're exactly equal in size. Similar triangles have the same shape, but different sizes. We talked about all kinds of things, but that gives you a really good background for geometry that we will be able to expand upon next week when we talk about area and volume. If you've got questions, definitely reach out and let me know. I hope this helps and enjoy the homework.